Designing slope stability in earthquake-prone areas. Welcome back to Blueprint to Reality, the channel where we break down the world of civil and structural engineering, turning complex concepts into simple, real-world understanding. Today's topic is one of the most critical challenges in geotechnical engineering, designing slope stability in earthquake-prone areas. Introduction. When we talk about landslides, many people think of rainfall or erosion. But in earthquake-prone areas, ground shaking becomes a leading cause of sudden slope failure. Even slopes that appear perfectly safe can collapse in seconds when seismic forces act on them. In this video, we'll explore how engineers analyze and design slopes that can survive earthquakes and protect communities from disaster. 1. What makes earthquakes so dangerous for slopes? Earthquakes send powerful vibrations through soil and rock. These vibrations can cause sudden loss of shear strength increase in pore water pressure cracking, and deformation liquefaction in sandy soils. As the shaking continues, the stability of the slope decreases, making it susceptible to sliding or total collapse. 2. Key factors engineers analyze. Before designing any seismic-resistant slope, engineers must study several important factors. Slope geometry. The height, angle, and overall shape of a slope determine how forces will act during shaking. Soil and rock properties. Engineers test key parameters like cohesion, friction, angle density, permeability, liquefaction potential. Groundwater levels. High groundwater greatly reduces stability during earthquakes by increasing pore pressure. Seismic hazard level. This includes a peak ground acceleration, PGA, and seismic coefficient, which represent the intensity of expected shaking. Past landslide history. Old failure zones are highly vulnerable to reactivation during earthquakes. 3. How engineers analyze seismic slope stability. There are several analytical methods used to understand how a slope will behave during an earthquake. Pseudo-static analysis. A simplified method that applies horizontal seismic forces using a seismic coefficient. Newmark displacement method. Predict how much a slope will move or slide during shaking, commonly used for embankments and earth dams. Finite element analysis, FEA, a detailed computer simulation that models stress changes and deformation during earthquakes. Limit equilibrium methods, used to determine the factor of safety and identify the most critical slip surface. Together, these methods help engineers make informed decisions about slope design. 4. Engineering solutions for slope stability in earthquake areas. To strengthen slopes against seismic forces, engineers use a range of stabilization techniques. A. Modifying slope geometry. Flattening the slope. Gentler slopes experience less shear stress and perform better during earthquakes. Benching. Cutting a steep slope into steps reduces the chances of large-scale sliding. B. Drainage control. Water weakens slopes significantly. To reduce pore pressure, engineers use horizontal drain subsurface drainage surface channels dewatering systems. Good drainage is one of the most effective ways to improve seismic stability. C. Reinforcement techniques. Retaining walls, gravity walls, cantilever walls, and reinforced earth walls support unstable soil. Soil nailing. Steel bars inserted into the slope increase resistance to sliding. Rock bolting, used in rock slopes to lock fractured rock masses together. Geotextiles and geogrids, increase tensile strength and distribute loads. D. Ground improvement methods. These techniques strengthen weak soils. Compaction, grouting stone columns, deep soil mixing. They are especially useful where liquefaction is a risk. E. Vegetation and bioengineering. Plant roots bind the soil and help prevent shallow slide failures. This is a sustainable option for low-risk slopes. 5. Special design considerations in earthquake areas. Engineers add extra measures when designing in seismic zones. Higher factors of safety redundant stabilization systems designing for aftershocks, not just the main quake monitoring tools like inclinometers, piezometers, and drone surveys emergency drainage systems. These ensure long-term slope safety and better performance during earthquakes. Designing slopes in earthquake-prone zones is a complex but essential task. By understanding soil behavior, seismic forces, drainage, and reinforcement methods, engineers can create slopes that remain stable, even during powerful earthquakes. It's a combination of science, engineering judgment, and practical experience. Thanks for watching Blueprint to Reality. If you found this video helpful, make sure to like, subscribe, and share to support more engineering content. Drop your next topic request in the comments. And as always, keep building the future one blueprint at a time.